Welcome to True Projects. In this video, we are going to explain about the project entitled as Source Code Error Understanding using BERT for Multi-Label Classification. So before getting into the video, let me give you the brief description about the project. This project focuses on using BERT and powerful NLP models to understand and classify source code errors automatically. It treats error analysis as a multi-label classification problem where snippet or error message can belong to multiple error categories at once. By learning contextual patterns in code and error logs, BERT helps improving accurate error detection, debugging, and developer productivity. Coming to the abstract, this abstract describes a project aimed to improve how source code errors are analyzed during software development. It highlights the limitations of traditional rule based and manual debugging methods, especially when dealing with complex or multiple errors at once. To address this, the project uses a birth based multi label classification model that can understand the context of compiler or runtime errors messages and assign more than one relevant error category. By leveraging BERT's deep contextual learning, the proposed system enhances accuracy, automation, and scalability, ultimately helping developers debugging faster and make better development decisions. Coming to the existing system for source code error understanding mainly relies on rule based techniques, keyword matching, and statistic analysis tools to identify and classify errors. These approaches typically assign errors to a single category and fail to capture the deeper contextual and semantic meaning present in error messages. Since they depend on manual defined rules or predefined patterns, they are inflexible and struggle to adapt to new programming languages or emerging error types. Moreover, traditional machine learning models like Navy Bias and support vector machines have limited capability in handling multi label classification and often perform poorly when faced with complex or ambitious error description. Coming to the proposed system or base paper work, the proposed system uses a birth based deep learning model to automatically understand and classify source code errors messages through multi label classification. Error messages are first pre processed and then passed into a fine tuned birth model, which effectively captures contextual and semantic relationship within the text. Unlike traditional approaches, the system can assign multiple relevant error categories to a single error message, closely matching real world debugging scenarios. The model is adaptable, language independent, and scalable, leading to improved accuracy, better interpretability, and enhancing developer productivity. Coming to the dataset, the CodeNet Pi dataset is curated collection of Python source code submissions from online programming competitions designed to support research in code analysis, bug detection, and automated repair. It is derived from the larger CodeNet project but focuses exclusively on Python solution, providing both the code and detailed error related information. The dataset includes structured files like train.json, which contains individual code samples, their corresponding error labels, and metadata. This organization allows researchers and developers to train machine learning models for tasks such as error classification, transformer based bug detection, automated code repair, and understanding error patterns in programming. CodeNet Pi is particularly valuable for projects aiming to enhance intelligent code analysis and improve debugging techniques using deep learning approaches. Coming to the novelty or extinction or enhancement or improvement. As an extension, a robot A based deep learning model was implemented as part of the framework, achieving the highest overall performance compared to previously tested models. This demonstrates its superior ability to learn meaningful representations of source code and accurately classify errors. Next, the framework incorporates an explainable AI component using line. This provides transparent token level explanations for each model prediction, enhancing interpretability and helping users understand why certain errors are detected, thereby increasing trust in the system. And furthermore, a web based interface was developed using Flask, allowing users to interact with the model in a user friendly manner. This interface supports error analysis, visualization, and testing of code, making the framework more accessible and practical for real world usage. Coming to the flow of the work, first we need to import the packages. The framework begins by importing necessary packages and reading the train.json and test.json files. Datasets are merged and only Python programs are retrained for further processing. Next, processing and label engineering. Runtime error types are normalized and the k top frequency errors are selected while rare errors are grouped as other errors. Multi-label targets are created for execution errors, fine-grained runtime errors, and code change operations. Next, train, test, split. The dataset is split into training and testing sets, including both the original source code and their corresponding multi-label targets. This ensures proper evaluation during model training. Next, text or code encoding. Source code is tokenized using models such as BERT, Robot A, Code BERT, and Code T5. Turn catcher and paddling are applied to standardize sequence lengths for model input. Next, embedding generation. For birth cost, and robot A, embeddings are learned via end-to-end fine-tuning. For code birth and code T5, hidden states are extracted and meaning pooled to create vector representations. Next, model training. Deep learning models are trained using binary cross entropy laws. Classically, machine learning models like random forest, KNN, and decision tree are also trained with an optional soft voting ensemble combining classical models. Next, prediction and thresholding. Model outputs are passed through a sigmod function, converting probabilities into binary labels with a threshold of zero point 0.5 for multi-label classification. Next, evaluation metrics. Models are evaluated using macro and weighted precision recall FN score, extract match accuracy, average label accuracy, Hamming loss, and ROC AUC for each label. Next, model comparison. Performance results are stored for all models, comparison tables are generated, and performance graphs are plotted to identify the best performing model. Next, explainable AI. Lime is applied to the trained robot A model to provide token level explanations highlighting influential parts of the source code that impact the predictions. Next, interface. New source code can be inputted, and the trained model predicts runtime error categories and suggested code fixes. Multi label predictions are returned for user interpretation. And finally, we have the model saving. Trained tokenizers embedding models and classifiers are saved for reuse, supporting future interference and deployment without retraining. Coming to the front end, a Flask based web interface with SQLite authentication allows users to input code with a pre processed and fed to the trained model. The prediction results are displayed inactively through the front end. The algorithms used in the project are deep learning models are of birth cost, robot A, loss function we have used binary cross entropy. And for classical machine learning, we used random forest, k nearest neighbor, and decision tree. An ensemble model we have used soft voting ensemble of classical models. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite tree. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap. 4. To execute the project first, we need to open the code folder which contains project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Model files. These are the files which contain the algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome, so that this is a home page should now be displayed in the browser. This is the front end built using Flask framework. In this page we have home button and in this page, we have home button and sign up button. Firstly, click on sign up button so that the user login account will be open where you need to enter the details for user authentication like username, full name, mail ID, contact number, and a strong password. Again, you need to confirm your password, then click on sign up so that all the given details are stored in signup.db and login.html page will be open where you need to access the application by entering the username and a password. Then click on login so that the login is successfully completed. In this page, we have error prediction button, graphs button, notebook button, and sign out button. Firstly, click on error prediction button. When you click on that, the error understanding with BERT form will be open where you need to enter your source code snippet or error message below to predict the possible error categories. So let us enter the source code or error message. The message has been entered and click on predict errors. The output is displayed as like input code or error message which we have given. And here we have the prediction results like runtime error. The confidence score is 0.9993%. Error type error is of 0.9997%. And a replace confidence score is of 0.9979%. And we have the line explanation graph here and click on back to home so that the form will be opened again. You can give the input and predict the errors. Now click on graphs button so that the graphical representation of the project will be opened. Now let us check one by one. First we have macro matrix comparison across model graph. The graph compares macro precision, recall and FN score across different models and ensembles. Overall, ensemble approach generally outperforms single models with extra robot with extension of robot A achieving nearer perfect score across all metrics. Recall tends to be lower than precision for most models, indicating some classes are harder to capture consistently. Next, we have weighted matrix comparison across model graph. The graph shows weighted precision, recall, and FN scores across models where performance is influenced more by majority classes. Ensemble models and hybrid approaches generally achieve stronger and more balanced weight scores than individual models. Extinction Robot A clearly outperforms all others, reaching nearer perfect results across all weighted metrics. Next, we have macro F1 score comparison model graph. The graph compares macro F1 scores across models, highlighting performance balance across all classes. Ensemble models generally improve over single classifiers, while Extinction Robot A stands out with a near perfect macro F1 score, lower scores for other models indicating challenges in handling class imbalance consistently. Next, we have exact match accuracy and average label accuracy comparison graph. The graph compares exact match accuracy and average label accuracy across different models. Most models show high average accuracy but low exact match accuracy, indicating partial correctness in common. Extinction Robot A stands out by achieving very high exact accuracy, while BERT cost performance weakest overall. Next, we have exact accuracy versus Hamming loss comparison graph. This graph shows an inverse relationship between exact accuracy and Hamming loss across models. Models like Extinction Robot A achieves nearer perfect exact accuracy with minimal error, while others have lower exact accuracy and higher Hamming losses. This indicates that stronger models make fewer label wise mistakes and more fully corrected predictions. Then click on sign out. So finally, this project demonstrates that birth-based models can effectively understand and classify source code errors in a multi-label setting, capturing both runtime error types and code change operations. The integration of deep learning with explainable AI enhances model interpretability, providing token level insights into predictions. Overall, the framework offers a robust solution for automated code errors detection and repair, supporting more intelligent debugging and code analysis. So, this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.